In the last lecture we have seen that operation of the gradient operator on a scalar field function. So this is the field of potential, this is the field of the temperature. Here temperature is maximum, darkness represent basically to the maximum temperature. Here dark spot basically represent to the higher potential. So when we take these potential and this temperature is a scalar, and this area basically represent to the temperature field, here represent to the potential field. So when we take the gradient of this scalar field function, we get the vector quantity. And similarly from here, when we observe the operation of the gradient operator on this potential, we observe basically a vector. So what was the meaning of this result? So basically the vector quantity represent to the magnitude and direction. So if you suppose you want to take the gradient at this particular point of the temperature, you are basically getting the magnitude as well as of the direction, and direction represent to the higher temperature. So this is the physical meaning of the gradient operator at temperature and at potential. In case of potential, suppose you take the gradient at this particular point, so you can basically measure the potential at this particular point, and the direction of that will be towards the higher potential. So interpretation of the gradient operator when it operates on any scalar field function, basically this shows the direction basically indicate to the higher values. And then after we have seen the operation of the divergence operator, and we take the divergence of any vector field, whether that is electric field or magnetic field. So we observe some mathematical result. This divergence of the E is we have seen that was a scalar quantity, that means magnitude only. If I take the divergence of electric field at this particular point, if I take the divergence here at this particular point, if I take the divergence at this particular point, so that observation will be different at every point. In case I measure the divergence here, the result will be positive. If I take the divergence here, divergence will be negative. If I take the divergence of electric field here, so divergence will be 0. So now this mathematical result, result is positive, result is 0, or result is negative, what basically we can interpret basically from these results, from these mathematical results. So from this physical picture, this meaning is very clear that this is a positive charge. Electric field lines basically are emerging from this, and this behaves like a source. So electric field lines are coming outward. Outward is used in reference to this closed surface, and these electric field lines travel into the space, and these electric field lines basically reach up to the negative charge and travel into this space till that they cannot find this negative charge. So this behaves like a sink. The electric field lines are converging here. So when I take the divergence here at any point on this surface, I observe that my result is negative. It means the characteristics of that field is basically defined through the result. Here the flux will be inward, here the flux will be outward. So emerging and converging. So when I get the result 0, it means total electric flux through the surface which I have chosen here, that is basically equal in amount to the input flux. The flux which enter through this open surface are equal in amount which are coming from the other faces of this open surface. But in these two situations, electric field, basically this is a source. From here electric field lines are coming outside, so we are just measuring that. Here in this situation electric field lines are entering through this closed surface, so divergence is negative, divergence is positive. But in this situation where our surface is open, the electric flux basically enter through this and coming out from the other face, so that is equal. Amount of the electric flux which enter through the one face is equal to the amount of the electric flux from the second face. So that's why total divergence that will be equal to 0. And this was the physical meaning, physical interpretation of the two operators. First was the gradient operator, second was the divergence operator. And gradient operator always operates on the scalar field function. Rest of the two, divergence and curl, operates on the vector field function. Now in our case the vector field function are electric field and magnetic field. So we have seen the observation of divergence. When we take the divergence of electric field or magnetic field at any point, so we are just getting a scalar quantity, just only magnitude, but on the basis of that magnitude basically we have to interpret about that field, the nature of the field, the nature of about the electric flux and magnetic flux that is coming or entering in through the surface. So with the help of these two mathematical operators we can define that. And the third one is the curl, curl of the vector fields. So it is not necessary that the electric field lines from the charge, suppose if this is our positive charge, so these are the electric field lines. If you see carefully, these are in a straight line form near to the charge, but these electric field lines travels into the space. If suppose negative charge is kept here at some distance from this positive charge, what will happen? These basically electric field lines travel into the space. These are almost in a straight line form, but these electric field lines are in a curved shape. The electric field line basically away from the positive charge or negative charge are in a curved shape. So now how to measure this curl? How to measure this curve? Curvature is not a right word, but how to measure this curl? This is basically curl. These are the electric field lines and these are similar to a curl like this one. So how to measure this? For that purpose we use this operation of the curl operator. In case of electric field we will write E, in case of magnetic field we will write P. So what is the interpretation of the curl operator when this operator operates on any vector field function? In case of del cross E, what will be the result and what will be the physical meaning of this result when we take the curl? So curl is a vector operator basically that shows a vector field's rate of rotation. So with the help of this we can find out the rotation of the field and their rate, and in addition to the direction we can find out the magnitude also. So curl is a vector operator that shows a vector field rate of rotation and basically the direction of the axis of rotation and the magnitude of the rotation. So del cross E basically is a result of this del cross E will be a vector, and we know vector have direction and magnitude. So what will be the direction of that rotation and the magnitude at any point. So it is a vector product of del operator with the vector field function. Measure the vector field's tendency to rotate around a point. So that basically how much is rotating, the rate of rotation. So this is the physical picture of the field. This basically, in case of Ampere's law, this is a current carrying conductor, and magnetic field basically develops around this current conductor in this way. So here basically we can use the curl del cross B. This we can found the rotation, rate of rotation of this field. With the help of this curl we can find out the rate of rotation of this vector field, basically magnetic field. So with the help of this operation, with the help of this curl operator, we can find out the rate of rotation of this field, direction as well as magnitude at any point. We can find out the magnitude at this point P1, we can find out the magnitude and direction at this point, we can find out the magnitude and direction at this particular point, or at any point into the space where we observe that particular field. So from the curl basically we are just measuring the rate of rotation of that particular field. How to write mathematically this curl operation on any vector field function? So for that purpose we are writing here this vector f, that is a field function. F1 is field component along the x-axis, F2 is the field component along the y direction, F3 is the field component along the z direction, where these I, j, k are the unit vectors. So how to define this curl f mathematically? So curl f is equal to del cross f. You have to use this arrow because in the paper I have already bolded, but it is not appearing in proper form, so I am marking this arrow. So curl f is equal to del cross f. So how to write basically this mathematical formula in a proper way? So first of write, this is a determinant in the first row basically for the unit vector I, j and k. Second row for the partial differentiation with respect to x, with respect to y, with respect to z, and third row basically this for the field component which is given correspond to that field. So for f, f1, f2 and f3 are given, so we are writing here f1, f2, f3. Now you can expand it about I, then del upon f3 upon del y minus this del f2 upon del z, then after this minus j, leave this column, this row. So this operation del f3 upon del x minus del f1 upon del z plus k, this is the minus, plus minus plus k, the expansion of this basically. So now for this with respect to this k, leave this row, leave it in this column. So del upon del x into f2, f2 upon del x minus del f1 upon del y. So this is the expansion of the curl f. So if any vector field function is given in terms of the component f1, f2, f3, then you have to write those component here. If suppose f2 is not given, in case so f2 is equal to 0, then you have to write 0 here. If f1 and f2 is given, then you have to write only these two, then time f3 will be equal to 0 if there is no k component in this case. So you have to make sure basically before solving this mathematical formulation, first check the component of this vector field. How many component is given? 1, 2 or 3, or all these three are given, then you have to write all these three here. If only one, then you have to write only one. If only two, any two, f1 f2 or f1 f3 or f2 f3, any two, then you have to write only those two. So this is the mathematical process to solve this curl f, and as a result you will basically what you are getting just a vector quantity in the direction of the rotation. And what will be the direction when you will find the result? What will be the direction? Here this basically this field is rotating about the x and y. This is the y axis, this is the x axis, and this one is the z axis. So you are taking the curl of B. This is your B, which is rotating. This field is rotating about x and y axis in this plane, xy plane. The magnetic field is rotating into the xy plane. So the result of this del cross B, the direction of this result will be perpendicular to this plane. So z will be the direction. So this will be the axis of rotation of that field. Z axis will be the direction of this result, and magnitude, which you have find out mathematically. So now there are two important points. What are those two important points? First, when curl f is equal to 0, that means there is no rotation. In the last case you have seen hurricane type of example or any type of rotations. In case of it, we are talking about the electrodynamics here, so we have seen that magnetic field lines from Ampere's law. So when there is no rotation, it means del cross f is equal to 0. So what will be the name, what will be called this f? This field function is said to be irrotational when this result is equal to 0. It means there is no rotation of the field. Irrotational field when curl f is equal to 0, and when divergence of f is equal to 0, this f is equal to 0. Here this curl f is equal to 0. If divergence of any vector field function is equal to 0, so you have seen this example. Where is the divergence 0? When you are using open surface and the flux which enter through the first phase is equal into the amount which are coming from outward direction, so from the other phase. So that means divergence f is equal to 0. So it is like a solenoidal. So this field basically is known as solenoidal. So there are two more scientific words here in the operation of these three operators. They, when curl f is equal to 0, that vector field function is known as irrotational, and when the divergence of any vector field function is 0, then that field is known as solenoidal. So these are the two more properties, two more important points in the operation of. Next point will be of two basic theorems, Gauss divergence theorem and Stokes